let me introduce our next speaker. We're very, very pleased to have Dr. Matthew Langholtz here today. Dr. Langholtz received his Bachelor of Science degree in forestry from, guess where? Oklahoma State University, and a Master's of Forestry and a PhD in Forest Economics from the University of Florida. He's currently in the Bioenergy program of the Environmental Sciences Division at Oak Ridge National Lab, where his primary research interests are in biomass resource economics, short rotation woody crops, and bioenergy from forest resources. His current research involves biomass feedstock supply and demand and sustainable forest management approaches to providing bioenergy feedstocks. Today, Dr. Langholtz is going to talk about the overview of the U.S. billion-ton update. Matt?
Does this mic work? I'm actually going to the browser, so. Thank you. I'm actually going to skip over here. A little unconventional format. Okay, great. It's a real pleasure to come back after graduating 18 years ago. My name's Matt Langholtz. I'm with Oak Ridge National Lab, and I think in a sense Phil's presentation might be a good tee-up for thinking about feedstock availability. So I imagine Phil might want some feedstock to run his processes. So, and an excellent point, he says cheap. What we're going to get into a little bit is, yeah, there's plenty of biomass, but really, what's Phil going to have to pay for it is the real question. I wanted to start out by emphasizing that this was a truly collaborative project involving a lot of many institutions and a lot of people, a real team effort. And this report was in the works for 2 years before I came on 2 years ago. So I'm talking about the billion-ton update from the DOE, and I'll just get to it. So a little outline. So I'm going to start out, I think a good way to explain the billion-ton update is start out with a comparison with the 2005 billion-ton study. Talk a little bit about the methodology of the billion-ton update, an overview of the sorts of feedstocks that we looked at in the billion-ton update, and summary of our results, and teased out some specific results for Oklahoma. So starting out with a comparison, I imagine probably most people in this audience might remember the billion-ton study that came out in 2005. And the purpose of that study was to see if we could potentially have available about 1 billion tons, and I'm going to be talking in dry tons, 1 billion dry tons of feedstock that might be needed to displace 30% of our liquid fuels by the year 2030. And in short, Bob Perlak at ORNL and others who contributed to that effort, they identified close to 400 million tons of forest resources and close to 1 billion tons of agricultural resources with, yes indeed, probably more than 1 billion tons of feedstock that might be available to meet that target. But of course that begs the question, what's that feedstock really going to cost? So in short, the original billion-ton study evaluates how much supply might be out there, and in the update that came out, I think June of last year, we evaluate prices, and we well, I'll see if I can just run down the list here. So 2005 was basically a national estimate. It included no costs. We had no land use change modeling. It was kind of an evaluation of what's there now and what's probably going to be there in the future with no specific time horizon. We used data sets available at the time, and they put together some constraints to account for sustainability issues. So with the update, we'll be talking about the economic, I'll talk about the economic modeling that was applied in this study. But basically we applied a county level model, a model that runs at the county level, and we put together supply curves. So, you know, how much can you get for what price, or maybe vice versa. If you put in a price, how much are you going to get, how much feedstock you're going to get. The model is based on land allocation. So this is a model of land use change. It was simulated from 2012 to 2030. We updated our data sets, and we kind of re-emphasized and focused on more sustainability constraints. So a little bit about our methodology. Resource base, we're looking at about 500 million acres of timberland and about 90 million acres of additional forest land in the report. Federal is teased out, so you can look at it with and without federal forest land. And it also includes agricultural resources, so about 340 million acres of cropland, 40 million acres of idle cropland, and also about 400 million acres of pasture. So in general, the resources were the same as the original study, but we've added annual energy crops. We've added some conventional wood, and logging residues and forest thinnings have been combined into a composite harvesting operation. Generally the same sorts of feedstocks. So with the University of Tennessee, with Chad Hellwinkle and Danielle Ugarte, we apply PolySys, or Policy Analysis System. It's a linear program that seeks, optimizes with profit maximization for the landowner. So in short, we plug in USDA baseline projections, which includes export data, projected demand, and we plug in National Agricultural Statistics Service, the survey data, the agricultural survey data, and we include, on the forestry side, supply curves for forest resources, and basically this model maximizes profit to the landowner in an economically competitive environment with convention. And a constraint is that demand for commodities is met before biomass feedstocks are produced. And we have two scenarios. One scenario is the baseline scenario. And without going into a lot of detail, basically that's designed just to represent the current, I would say, state of productivity of agricultural resources. And I think it was in 2000, I think in 2000, there was a conference, a workshop held on the high yield scenario, and maybe some people here participated in that. But basically, there was an effort made to try to account for how much future yields might be improved to put together these potential high yield scenarios. And it's pretty important. It's a significant variable. As you'll see in the supply curves, if you compound improvements over the next 20 or 30 years, then future yields are significantly impacted by how much annual improvement potentially you get in feedstock. So for a research community such as this, these sorts of potential yield increases are really what could potentially drive the economic availability of feedstocks in the future. I think we'll see that here. So quick overview of the sorts of feedstocks that we're looking at, starting out with crop residues. With our time constraints, I won't dwell on this, but as you know, if you're harvesting the feedstock, there's some minimum tonnage per acre that you're going to need to pull off to make the harvesting operation economically viable. So your economics wants to drive that removal rate up. But obviously there are environmental constraints that might require you to leave feedstock on site to maintain soil organic carbon or prevent erosion control, that sort of thing. So there are these fighting factors, and another component of the research community that contributes to is agronomic strategies, be it precision agriculture, precision harvesting operations, improving yields, et cetera, that can drive this curve back up to where we have both sustainability and economically viable harvesting rates. So for example, the way this model runs on the residue side, we have spatially explicit yields of, for example, corn stover production. And then we have crop residue retention coefficients that are higher in arid areas and lower in the northern lake states, for example. So basically we're seeing a lot of higher residue availability in this area of the country. So if the purple and green, that's the high yield scenario, 4% that I mentioned a moment ago. This being straws, purple being straws and the green being corn stover. And the red is straws in the baseline scenario, and the blue is the corn stover in the baseline scenario. So you can see that we're looking at upwards of combined 300 million tons in 2030 on the high yield scenario, and approaching 200 million tons in the base case scenario in 2030. So again, another way of looking at this for the corn stover, we see yields, productivity increasing with time. 2012, 2017, 2022, and 2030. This is the base case. By the way, okay, so the y-axis is the price, and these are million dry tons. And in the high yield scenario, you can see just potentially by 2030, you have a lot more feedstock potentially available in the residues, corn stover. So the overview of the sorts of dedicated energy crops that we included in the update. So we include a wide range of potential dedicated feedstocks, annual and perennial, herbaceous and woody. And we assign productivity at the county level, and we also assign crop budgets at the county level in the economic model. So for 2017, 2022, and 2030, on the base case scenario for dedicated energy crops, we can see we're approaching 400 million dry tons at a price of $60. And again, with the high yield scenario of dedicated crops, we can potentially, by 2030, increase economic availability of feedstocks. Forest resources, Ken Skog from the Forest Products Laboratory of the Forest Service put together supply curves for forest resources. So basically the way this works is when we hit a certain price point, we tap into the supply curves for forest resources. And Ken put together composite supply curves where we have potential yields from thinning operations and potential yields from logging residues. And basically Ken assumes 50% might come from each in a combined silvicultural harvesting operation. So the forest residue supply curve is basically an average of the two. So the red line here shows the economic availability of forest residues on private land. And the blue line adds potential availability also from federal lands. A little bit controversial, this feedstock, but basically pulpwood is probably priced out unless you're really willing to pay pulpwood prices. but we do include some amounts of pulpwood in our feedstock assessment. It really doesn't come into play. Let me put it this way. It's probably more than Phil wants to pay for it. Okay, so summary and overview. So how much feedstock is really available overall? It really depends on what type of feedstock you're talking about, what scenario you're talking about, baseline or high yield, which type of feedstock, where you're interested in, etc., what year. So it really varies, like I say, by these different potential dials. So if you Google the billion-ton update, you can find the report, and you can get a lot of information there. If you Google the Bioenergy KDF, Knowledge Discovery Framework, you can query the data by scenario, by type, by state. You could construct your own supply curves. If you're interested in your own scenario, if you're giving a presentation, you want to make a case, or you want to make a point, evaluate potential, you can drill into the KDF. I'll be honest, it's not necessarily the sort of thing you're going to jump in 5 minutes, have what you want. It definitely takes some startup time. Go ahead and email me if you're not having luck with it. It's a relatively new web page, a new product. The interface isn't necessarily immediately totally intuitive, but please call me if you're interested in using it, because I think it's a good resource. But in short, there was some question last night at Giuseppe's. Are we on track to meet RFS2? I don't know about that, but is the feedstock there to meet RFS2? So these black lines are RFS2 targets. I think this one's actually off a little bit. It should be 22 gallons by 2022. But at any rate, the feedstock's definitely there. This is just the baseline scenario. The more you pay, the more you get. I don't know if Phil necessarily wants to pay $60. Probably not. Oh, by the way, these are farm gate prices. I should have emphasized that. So these are dollars per dry ton at the farm gate. So that does not even have haul cost on it. So the feedstock's there to meet our targets, and in the high yield scenario, it's definitely there if the economics can work it out. And that's something that I think, obviously, a lot of people are working on that, private and government, et cetera, needless to say. So how does this compare with the 2005 study? So in the 2005 study, kind of a base case yield of sorts, we were looking at about 1 billion tons. In the high yield, we were looking at more than 1 billion tons. With the update, because of increased higher constraints for sustainability to account for erosion control, soil organic carbon, et cetera, we actually have slightly less forest residues coming in this analysis, and we have slightly less ag residues probably coming in this analysis. By the way, this is just a placeholder of $60 a ton. But the dedicated energy crops in the update under these simulations more than make up for those lesser supplies on the residues side. So I took a stab at the KDF and I drilled in to Oklahoma data a little bit. I just started out. I just pulled out the base case scenario, $60 a dry ton, pulled out 2022. So you can see these different sorts of resources that come out here. Basically what we're seeing, I haven't heard of any major surprises coming out of our results as far as the state level resources. And I think we see, in the Southern Plains states, we see a lot of potential for the production of perennial grasses. No major supply there, no major surprise there. So I drill in a little bit and I put together some supply curves of the top 10 states that are likely to be producing perennial grasses in 2022. And for those of you who don't necessarily read supply curves all the time, less is better. Less price is better. You have more economically available feedstock. So for example, for Texas and Oklahoma and Kansas, we can probably get a lot of feedstock at a pretty low price, potentially. And when you account for, when you convert this to tons per square mile, Oklahoma looks even better. So those are the sorts of results that I think we're looking at this point. And that's it. Appreciate the opportunity.
Okay, thank you, Matt. Your question?
Yes.
The cutoff is at $40 a dry ton, and is that just the assumption that below there, no one is willing to commit to growing energy costs?
You know, I wonder if anyone in the room is an expert in switchgrass budgets. I don't know, but according to the budgets, I think you're pushing it to get $40 a dry ton delivered to the farm gate. That's not to say none's there. We get residues. We get a lot of forest residues at $20, $30 a dry ton. When we talk about a dedicated crop, that's what our budgets are generally reflecting. I think maybe, yeah, that's it. I mean, those are the budget assumptions that we have.
I think the only time we maybe will get below 40 would be if we capture what's on COP lands every few years rather than every year.
Yep. Sounds good. So there'll probably some niche circumstances where we can get something cheaper, sure.
So you have a lot of considerations with quantity numbers. Do you have any considerations of quality, feedstock quality in your updated report?
No, and that's an important point because certain feedstocks are going to have competitive advantages. I don't know if you're talking about post-farm gate or pre-farm gate, but either way, there are plenty of variables like that are going to influence demand for one feedstock over another. So if you look into the report, there's a text box where, for example, potentially woody feedstocks where you have more flexibility with your harvest window. You could harvest your woody feedstock year-round, whereas with your ag resources, you got that storage cost because you reduced harvest window. So potentially you could offer a premium. I don't know if Phil might have one feedstock flavor he prefers over another. And
that's what we're going to be learning.
Yeah. So this report should not be misconstrued to be projections of how things are going to happen, because there are going to be pros and cons of different feedstocks, and who knows what the future holds. But it's a stab at potential production. Yeah.
Quick question about the cost of the feedstock. Understood correctly, the researchers are asking for 1 to 4% increase in biomass yield. So why the cost keep going up? Even the biomass yield is going to go up.
Well, I don't know if it's necessarily that costs go up. I think, okay, so if you were to look at a fixed feedstock, for example, if I could back up a second. Going out on a limb here. Okay, so here we're saying at 2017 for $50 you can get 50 million tons. At 2022 you can get 150 million tons.
At the same cost, right?
At the same cost. Yeah. Yes.
Anyone done a study on past market and how that changes prospects for availability of feedstock, transportation being?
So we're feeding data into a multi-lab white paper to evaluate optimum biorefinery sizing, and we're passing these farm gate costs onto INL, who's going to tack on well, first of all, they're going to refine, if they want to, our pre-farm gate harvesting costs, and then they're going to tack on their post-farm gate transportation costs, and then we're going to reshuffle everything according to the cheapest price at the facility throat. So we're working on it. I believe other people are working on it. This study stops at the farm gate, but others have, and I think are. Phil's probably all over that, but yeah, it's definitely an important question. Yes?
If you look at the farmer's end, if you grow something in a square mile of corn and a square mile of bioenergy crop, even if you put it $80 per dry ton, how does it compare from farmer's perspective? What he makes it for a square mile of growing bioenergy crop or growing corn or something?
Could you repeat the question, please?
How much a farmer would make if you compare, if he grows a square mile of corn and he produces a square mile of dry ton of switchgrass? Do you make that kind of comparison?
I don't, but I want to say in a sense this model says let the most profitable feedstock win.
From the producer's perspective,
Yes, from the producer's perspective.
farmer's end.
Excuse me?
How about the farmer's end?
What's the difference between farmer and producer?
I mean, how much you would make comparison if you want to switch over to switchgrass instead of making corn?
Yeah. I honestly don't know, and it depends on the offered price. So our point is, how much price can you offer? If you offer 40, if you offer 60, I don't know. The price right now is, it's not there right now. Would be my answer, I think. Yes.
So this model, though, the reason that you get more energy crop when it's $60 a ton is that it assumes farmers will switch from something else to growing an energy crop, right?
Yes.
Right?
Yes.
But the model also limits how much you can switch out of food. What are those?
Okay, so first of all, USDA baseline demand projections are required to be met first. For food production, yeah. So as far as food versus fuel, the constraint is that food is met first. It'd be interesting to relax that constraint and see what happens. I don't know. And further, there's also a further constraint that no more than, I believe, 25%, there's a cap on 25% land use change within a given county, I believe is the constraint. So there are other dials in there that one could play with.
That's just an artificial one that you put into the model.
Yeah.
Okay, one last question. You talked about transportation costs being different post-peak. Where does storage fit into this?
It's a cost. So basically, for example, when we hand off our data to INL so they can do a biorefinery sizing study, we might have to tack on storage losses on top of that. So we account for, I think it's 3% losses from the field to the gate. They might want to tack on another 3% losses. That's a cost. I think that's the main cost is some dry matter loss from storage.
Energy costs or chemical costs in storage?
Well, INL, when we pass on our data, they're going to tack on their budget to haul it off. So I was talking to, I had a conference call last week with INL, and they're talking about what it's going to cost for them to pick it up and take it to the next step. I don't know if that answers your question, but.
I was up with INL a few months ago, and they're looking a lot at transportation, and for things like the herbaceous materials, the question is you're going to have to go to something like pelletizing in order to maintain longer-term storage. I don't think there's a conclusion there, but that certainly brings in added energy costs.
Yeah, 6% loss total seems a bit on the low end, but I see.
It could be.